For the do now, this is a voltaic cell consisting of zinc and zinc 2+ and copper 2+ is constructed. At standard conditions, the overall cell potential is 1.10 volts. The same cell is constructed with different concentrations. If Zn2+ concentration is 0.2 molar and Cu2+ concentration is 0.7 molar, how does the cell potential compare to the standard cell potential? And what I did is I gave the equation here. Here is the standard cell potential, so that not symbol means standard. It gives us delta G, it gives us the equilibrium constant. And then there was this table just to be helpful in comparing cell potential to standard cell potential. And remember, standard. So when it says standard conditions, that means that all of your concentrations are 1 molar. So that means that the Cu2+ concentration was 1 molar, the Zn2+ concentration was 1 molar. Zinc and copper, those are solids. They don't have concentrations. And so remember, when we're at standard conditions, Q equals 1. At standard conditions, Q equals 1. Because it's 1 molar for every solution. Now, if it says that we construct the cell with different concentrations, so now we're not at standard anymore. When you change anything about a voltaic cell, really when you change anything about any electrochemical cell, whether it's voltaic or electrolytic, when you make changes, calculate Q. Remember, we compare Q to 1. So if I calculate Q for the non-standard conditions, well, Q is products over reactants. These are solids, so they're not included. So Zn2+ is 0.2 molar. Cu2+ was 0.7 molar. So if we want the exact concentration, we could plug it in our calculator. We can see here, though, 0.2 divided by 0.7 is less than 1. So if this were a multiple choice question, you wouldn't even need to plug this into a calculator because you can see 0.2 divided by 0.7 is less than 1. If we want the actual value, it's 0.286. So Q is less than 1. I still have this up on the board from last week. If you increase Q, you decrease cell potential. If you decrease Q, you increase cell potential. So when we compare Q at non-standard conditions, we compare Q to 1. So if we look down here, this cell that was created actually fills in or goes along with Q is less than 1. When Q is less than 1, the cell is farther away from equilibrium than at standard conditions. Because remember, the goal to get to equilibrium is to have Q equal K. Look how big this equilibrium constant is. When Q equals K, the cell is at equilibrium. Remember, equilibrium is where batteries go to die, so the voltage is 0. But if Q is less than 1, we are even farther away from this value of K. When Q decreases, we're even further away from the equilibrium constant. So since we're farther away from equilibrium, we expect cell potential to increase. I'm just going to say E will increase. Notice it's just E and not E naught. E is cell potential. That's cell potential at any conditions. E naught is only if you're at standard. When Q equals 1 here, when Q equals 1, your cell potential equals your standard cell potential. But since Q is less than 1 here, the cell is farther away from equilibrium, and so your cell potential will increase in order for the cell to run longer, to increase Q until eventually Q equals K. So this was just a do now question to review non-standard conditions. And remember, if you make changes to a cell, calculate Q. When you make changes to a cell, you want to calculate Q. Compare Q to 1. So what we're going to do is talk just a little bit about this week, and then go through some examples for today. So this week we're going to finish up Unit 10. So since we're finishing up Unit 10, that means we have mastering due. So remember, mastering is due tomorrow. And then along with mastering, our Unit 10 test, so on electrochemistry, redox and electrochemistry is Thursday. Today we'll finish up examples. You work on mastering. Tomorrow we'll go through some pre-response questions. Wednesday being a 2-hour delay day, we'll do lab. So I have a short electrochemistry lab that we can do. Remember, practice and class videos are all under the Unit 10 materials in classrooms. So any of the videos from class, recorded examples, things like that are on Classroom, any practice that we've done. A lot of the review material is posted to the class website. So I'll give you guys a review tomorrow. Answers to the review, there's a video, answer key to the review. That is all on the class website, not on Google Classroom. Just some more info. We had one review session Saturday. The next one is next Saturday, so not this week, but the following, so the 24th. Same thing with the bonus. If you did not attend Saturday, so you worked, you had practice, right? There's some reason that you couldn't attend. There is info on Google Classroom. You weren't able to attend, but you still want that bonus opportunity. So just take a look it's under AP exam review. There's a topic under the classwork tab that's AP exam review. Take a look at that. I have the recording from Saturday, so you'll go through, you'll watch that, answer some questions. The Electrochem quiz. So you guys had an Electrochem quiz last week. I did post some information on Classroom. If you didn't do as well as you hoped, there is a retake available either today or tomorrow, so you'll take it during your study hall. If you are interested in the retake, I know I got some emails yesterday, just let me know which day and what period. So whether you're in person, I can write you a pass. If you're online, I'll send you a Google Meet link. So just make sure that if you're interested in that, it can replace your score. We've done that a couple of times already. Any questions on what we're doing this week? Okay, so what we're going to do for just a little bit of time is we're going to talk about the problems that go along with electrolysis. So if you don't have your notes out, you want to get out your notes. We're going to be focusing a lot on page 17. So the notes for this are on 16 and 17 both. 16 is where we had all of the general information, and then 17 is where we have all of our examples. So we talked about electrolytic cells last week. The biggest thing with electrolytic cells is looking at the application. So actually applying electrolysis to the real world. And the most common application of electrolysis and electrolytic cells is electroplating metals. So what that means is we actually connect these wires to a battery. We make a non-spontaneous reaction work. And what actually happens is we're able to plate a metal onto some object. So if you've seen, you have a gold-plated piece of jewelry, or you have a silver spoon, a lot of times it's not full gold or it's not fully silver. It's simply a layer of the metal plated on the outside of the object. And so what we look at with these electroplating examples are these stoichiometry problems that go along with it. So a lot of this is in your notes already. I just tried to summarize some stuff from the video. When it comes to looking at electroplating, we can look at the amount of charge. Now I know Q we've used before as variable for heat. When we're dealing with electrolysis, Q actually represents charge. So we look at the relationship between the amount of charge that flows. We look at the current, which is represented by a capital I, and we look at the time that the cell operates. The equation I equals Q over T is on your equation sheet. So on your equation sheet on the back, under thermodynamics and electrochemistry, you have I equals Q over T. And remember, over on the side, you have what all of the variables represent. I is current, Q is charge, T is time. And so when we look at Q, it's charge in coulombs, T is time in seconds. So current in amp is actually a conversion factor that we use. We're going to be using amps as a conversion factor on a lot of the questions that we do today. This is nothing more than dimensional analysis. So a factor label method. We have to pay attention to units. We have to make sure everything cancels. We just need to make sure everything is set up correctly. So current is the conversion factor that allows us to go between coulombs and seconds. Time needs to be in seconds because our conversion factor has that. Faraday's constant, remember, is on your equation sheet, 96,485 coulombs per mole of electrons. So that is also a conversion factor. It allows us to go between charge, coulombs, and moles. And then we just have to pay attention to moles of electrons. So we actually have to look at half reactions that are being used in these electroplating problems. So what we're going to do is we're just going to jump into an example. So example 6 is on page 17. So examples 6, 7, 8, and 9 that we're going to look at today are all on page 17. So this question, and we see these both in free response and multiple choice. So these could be free response or multiple choice questions. So if we take a look at this, it says how long. So how long means I'm solving for time. And my answer should be in some unit of time. How long must a current of 5 amps be applied to a solution of Ag plus to produce 10.5 grams of silver? So when we have questions like this, and we see current, and we see mass, or we see time, you want to go through and you want to label everything that you have. 5 amps. Current. So amps are the unit for current. When we see amps, I recommend writing out the conversion factor that we're going to use. Amps are coulombs per second. So 5 amps are 5 coulombs per second. Per second would just mean per 1 second. So there's a conversion factor. And then you always want to make sure that you can determine the number of electrons. So we have a solution of Ag plus, and we're producing silver. So we're just producing Ag. This is nothing more than balancing this half reaction. When I say balancing the half reaction here, you're just adding electrons to one of the sides. So this side is +1 because it's Ag plus. This side is 0. There's no charge up here. So if this is +1 and this is 0, remember you add electrons to the more positive side. How many electrons do I need to add to make this side equal 0? Just 1. So if it helps you to just put 1 E minus instead of just E minus, that's fine. We're going to need this half reaction because this tells us how many electrons we need. Typically, your given information for this dimensional analysis problem is either time or mass. Since I'm solving for time, that's what I'm ending with. Here's my given information. That's what I'm starting with. 10.5 grams of silver. Amps is a conversion factor. Coulombs per second is how we can go between coulombs and seconds. So I need to get from grams of silver all the way to time. I'm going to write another conversion factor up here from our equation sheet. Because remember, that 96,485 coulombs per mole of electrons. So what this means is that for every 96,485 coulombs, there's 1 mole of electrons. So there's how we can go between moles and charge. So we have 2 different conversion factors that we can use, but now we need to start by figuring out, well, what do I do first? Well, for any stoichiometry problem, you start with grams. What should we go to first? Moles. I highly recommend that you always label with a substance. So it's grams of silver to moles of silver. So this is probably the first time in a while that we need a periodic table. 1 mole of silver is 107.87 grams. 107.87 grams per 1 mole. So now my grams of silver have canceled and I'm at moles of silver. So then you want to think about, okay, what should I convert to next that I could use one of these 2 conversion factors? Well, I'm still in moles. I need to cancel moles of silver. Well, I noticed that to use Faraday's constant, I need to get to moles of electrons. Well, this is nothing more than a mole ratio of a balanced half reaction. For every 1 mole of silver that is created, how many moles of electrons do we need? Well, just 1. This is a mole ratio from the balanced half reaction. So now moles of silver cancels. Now that I'm at moles of electrons, you can see why labeling is useful because you went from silver to electrons here. Now that I'm at moles of electrons, I can go to charge. For every 1 mole of electrons, 96,485 coulombs. This is Faraday's constant. This is a constant. This never changes. That's on your equation sheet. So now our moles of electrons have canceled. We're at coulombs. My goal, again, is to get to time. Well, now this is where current comes in. Current lets us go between charge and time. For every 5 coulombs, because if it's 5 amps, that means it's 5 coulombs per second. So for every 5 coulombs, it takes 1 second. Now, because it didn't specify time, leave it in seconds. So this becomes nothing more than a stoichiometry problem, a big dimensional analysis problem. So we can plug this into our calculator. And make sure if you're plugging this in as well, that we're getting the same thing. So you multiply across the top, you divide by everything that's on the bottom, so make sure you're using parentheses if you like to do it all at once. Here, should have used minutes. 1,878. If it wants 3 significant figures, so this will just practice with sig figs. 3 sig figs means I need to round to the tens place, which would be 1880 seconds. Because remember, trailing zeros are not significant unless there's a decimal. So in this 5 amps, these are trailing zeros, but because of the decimal place, they're significant. Now, if it said how long in minutes, then you would just take your seconds and you would convert to minutes. So doing these electroplating questions, it's just a big dimensional analysis problem where we're using lots of conversion factors to go between grams of something or moles of something to time. As you take a look at example 6, any questions as to how we got any of those conversions. All right, so let's take a look at example 7. So example 7 says a solution of copper 2 nitrate, CuNO3 is electrolyzed to plate an object with solid copper. So what we do is we run an electric current through a solution of Cu2+. So we use a battery or we use another power source to run current through a solution, and we're able to actually pull out solid copper. So the current of 1.2 amps, so capital A is amps, is applied for 10 minutes. Determine the mass of copper plated. So now my goal is to solve for mass. Mass means we're looking for what unit? Grams. So we want grams of Cu at the end. So let's think about what we're given here. I like writing everything out that I have first, then I'll do the whole problem. So 1.2 amps. Remember, current is a conversion factor. If you're like, how am I supposed to remember that amps is a conversion factor? Well, on your equation sheet, remember you have I equals Q over T. And over on the side, it says I is current in amps, Q is charge in coulombs, and T is time in seconds. So the equation sheet tells you I equals Q over T, which is coulombs over seconds. So the equation sheet even reminds you that amps are coulombs over seconds. So 1.2 amps is 1.2 coulombs per second. Well, per second means per 1 second. It's applied for 10 minutes. Well, that's not a conversion factor, that's just given information. So that's what I would start with, 10 minutes. Now there are some other things that we need first before we continue on with this. The next thing is to remember that we always have Faraday's constant, 96,485 coulombs per mole of electrons. Per mole means per 1 mole of electrons. And because we're dealing with electrons, we need to make sure we have a balanced half reaction. So the goal is to plate solid copper. So Cu is my product. And it says a solution of copper 2 nitrate. If it's copper 2, what's the charge on that cation? 2 plus. So the half reaction that we're dealing with here is Cu2 plus to Cu. How many electrons does Cu2 plus need in order for this half reaction to be balanced? 2. Because when we add 2 electrons to 2 plus, that brings the charge down to 0, which matches up solid copper. So now we have conversion factors that we might need. We have our half reaction that tells us the number of electrons we need. So now let's start working through this entire dimensional analysis. So notice here, I always like looking at everything that I have. I say, okay, 10 minutes. Well, before I can use any conversion factor, what do I need to convert minutes to? Seconds. So I'm going to start by converting from minutes to seconds. 1 minute, 60 seconds. My minutes have canceled. Now that I'm at seconds, look at everything you have here. Here's my conversion factor that has seconds in it. I can go between seconds and charge using the current. For every 1 second, it's 1.2 coulombs of charge. So again, I'll just label the conversion factors that we're using. Here's our current. So now we have coulombs. What could I use next to cancel coulombs and try to get closer to mass? What we have here, we've already used this one. We can use Faraday's constant. 96,485 coulombs per 1 mole of electrons. So again, this is Faraday's constant. Faraday's constant. So now our coulombs have canceled. This is why our balanced equation is important, the half reaction. Because here is a mole ratio. To go from moles of electrons to moles of copper, we need a mole ratio. So for every 2 electrons, there's 1 mole of Cu. Because mass of copper plated, we're looking at Cu solid. And then to get to grams, we'll go from moles of copper to grams of copper. For every 1 mole, we can look at the periodic table. Copper's atomic number is 29. 63.55 grams of copper is 1 mole. So again, I'll finish labeling this. So here was our mole ratio. Here is our molar mass. So we can plug this in. And 2 sig figs, really. So I get 0.237. If we stick to sig figs, these are both 2 sig figs. So then we would get 0.24 grams of copper. 0.24 grams of copper. So you can see we use current and Faraday's constant as conversion factors here. You need a half reaction to make sure you know how many electrons you need. And then we use our periodic table for the molar mass. So I want you guys to see if you can go through example 8. So see if you can use what we've used so far. Before you work through the entire problem, focus on what your conversion factors are. Make sure you have your balanced half reaction. And then you can set everything up. So work through example 8, and we'll see if we get the same answer. Okay, so I got 229.6. So if you see what I did up here, I went from grams to moles of gold. 1 mole of gold needs 3 moles of electrons. So I wrote my half reaction before I even started, because it's very easy for people to skip this step. And if you skip this step many times, you're not going to get the right answer. Then I went from moles of electrons to coulombs using Faraday's constant. And then from coulombs to seconds using the current. Now I got 229.6. Technically, we need 3 significant figures. So 3 significant figures, I would actually round to the ones place. But the 6 will round this up to 230. Now, right now, this is only 2 significant figures. Here's how you could actually do 3 sig figs. And a lot of times you'll see this in AP questions. They just put a decimal after the 0. You don't need anything after the decimal. That decimal point right there means that every one of these numbers is significant. Now, if you rounded to 4 significant figures, would you miss this? Probably not. But it's good to practice with significant figures. So this takes 230 seconds. Again, it just says time. So if you went to minutes, that's okay. But you need a unit. If you just did 230, I don't know if that's seconds or if that's minutes. So don't forget units as you work through this as well. So the last question here is multiple choice. So we're going to practice without a calculator. Because remember, on the multiple choice, you're not going to get a calculator. So I'm going to show you some tips and tricks for doing multiple choice. Now this question is also a little unique because it gives us a unit that we haven't seen yet. So it says, in the electroplating of nickel, 0.2 Faraday of electrical charge is passed through a solution of nickel 2 sulfate, NiSO4. What mass of nickel is deposited? So a couple things as we look through this. 0.200 Faraday. Well, we've seen Faraday's constant. A Faraday is nothing more than moles of electrons. So 0.2 Faraday of electrical charge means 0.2 moles of electrons is passed through a solution. Why can they not just say moles of electrons? Well, because they have to give a unit to everything. So 0.2 Faraday is just moles of electrons. Passed through a solution of NiSO4. So again, we need a half reaction. So I know that SO4 is -2, so Ni must be +2. So here we have Ni2 plus yields Ni. We're taking the cation, reducing it to form the solid. Well, you need to make sure that it's balanced in terms of charge. So we need 2 electrons for every 1 Ni2 plus cation. The question says, what mass of nickel is deposited? And a lot of times people see this question and they're like, okay, there are some things that were not given in this problem that we were given in problems before. But let's take a look at the setup and see if there's anything else that we need. So our given information is 0.2 Faraday. We've said that a Faraday is just a mole of electrons. So 0.200 moles of electrons. My goal is to get to mass of nickel. So grams of Ni. So right now I have moles of electrons. Well, I want to get rid of moles of electrons. I want to go to nickel. This is like a stoichiometry problem. I have moles of one thing, I need to get to the other substance, so I need the mole ratio. This is where your half reaction is needed. For every 2 moles of electrons, we will produce 1 mole of nickel. And then it wants grams. So for 1 mole of Ni, if we take a look at the periodic table, nickel is atomic number 28. It's 58.69 grams. Now again, this is multiple choice, so no calculator. Here's how we can do this without a calculator. We cancel where we can. I'm going to put this all into just one math equation, right? Mathematical problem. I'm just going to combine everything. So 0.2 times 58.69. 0.2 times 58.69, that's what I would do in a calculator, divided by 2. Cancel where you can. I see 0.2 and 2. Well, what is 0.2 divided by 2? Right? 0.2 divided by 2 is 0.1. Now I'm doing 0.1 times 58.69. 0.1 is 10%. Here's a little secret. Forget that I had this decimal here. What if it was just 1? What's 58.69 times 1? 58.69. But if instead of it being 1, I have to move the decimal place over once to the left, instead of 58.69, it's 5.869. Well, which multiple choice answer best fits what we just found? B. B. Now another way that you could do this, right, if instead of moving the decimal like that, you just want to round in general, instead of doing 58.69, use 60. 0.1 times 60 is 6. The only answer choice that's close to 6 is B. So when you have to do math in multiple choice, and we'll practice this more and more, especially as we start reviewing next week, we'll do a lot of doing problems without a calculator. So practicing with rounding and things like that. Any questions on any of the examples that we looked at?
I'm still confused on how you got the moles of electrons in the Faraday. Like, what?
Oh, so like
why?
Faraday is another word for moles of electrons.
I was like,
so like Faraday's constant is a separate constant. When you just have like 1 Faraday, that's 1 mole of electrons.
oh, okay.
Yeah. Faraday's constant, that's the 96,485. But just the term Faraday, you can replace with moles of electrons if it gives you a number like that. So if instead of this it said you had, 5 Faraday of charge, that's 5 moles of electrons of charge. Yep.
Okay.
Any other questions?